Welcome back everyone to our third and final lesson in Unit 2. Today's lesson is going to expand on our understanding of calorimetry. So today you're going to be able to use calorimetry to solve problems. And you should be able to distinguish between heat and energy and temperature, or that should say between heat energy and temperature in terms of molecular motion and amount of matter. So in our last lesson we talked about what H meant, and specifically what delta H meant, which is our change in heat during a reaction, either endothermic or exothermic. So the H just by itself represents the heat of reaction. Now this is a basic part of chemistry, is trying to understand energy changes that occur during any type of physical, chemical, nuclear change. And every physical and chemical change will be accompanied by some type of change in energy. It's either going to be released or absorbed. And this can be referred to in a few different ways. And we're going to call our heat of reaction, we're going to represent that with a capital H. And this is really going to represent the change in potential energy that's associated with a chemical or physical change. And that's really what we're going to be measuring, is the change in potential. Now again, this is a little bit of a review from our last lesson. So a positive change in potential energy indicated by a positive delta H. Remember the delta meaning change and the H meaning heat. So it's a change in heat. It's a positive change in heat, meaning that kinetic energy from the surroundings, or if we're performing an experiment or reaction in a calorimeter, in that case the water, so energy from the surroundings of the water is absorbed into that chemical or physical change, which results in greater stored energy and lower temperature in the surroundings. Now this can be done in a chemical change, which we're probably thinking of as more common, but this will occur in physical changes as well. Now, positive delta H means that we are going to absorb energy from the surroundings in order to occur, and this occurs when we, let's say, melt water from a solid to a liquid. We have to intake a net positive amount of energy in order to change a certain amount of solid matter into liquid matter. Liquid matter is moving faster than solid matter, which is moving slower, and it is allowed to move faster by absorbing heat from the surroundings. This could be picking up a snowball and holding it in your hand. The snowball is going to melt by absorbing heat from your hand as well as the surroundings. It's going to increase the kinetic energy, the temperature of all of the water molecules in that snowball. They're going to move faster, and when they move fast enough and gain enough energy, they are going to melt and turn into a liquid. Now this is known as endothermic change, and these reactions tend to feel cold. Now we're going to use Table I from your reference table today, and on Table I are listed several different reactions. On there they show you what the reaction is, and they give you the associated heat value, the change in heat when this reaction occurs as written. Now in this particular reaction, this says we're going to take 1 mole of nitrogen gas and 2 moles of oxygen gas, react them together, and that's going to produce 2 moles of nitrogen dioxide gas. And when we look at the delta H, or the change in heat value over here, it's a positive 66.4 kilojoules. Now in order for this reaction to occur as written, that reaction is going to have to absorb 66.4 kilojoules of potential energy from the surrounding environment. And the reaction can't happen until it does absorb that specific amount of energy. the potential energy is stored in between or within the covalent bonds between the nitrogen and oxygen atoms in NO2. When this happens, the surrounding temperature decreases as a result. So if you're holding the snowball in your hand, and let's say we assume all the heat is going from your hand into the snowball, the temperature of your hand is going to decrease. So you take the snowball away, your hand is cold. And that's not necessarily because you are holding a cold snowball, but remember that heat moves from where it's hot to where it's not, and your hand is cold because there's such a large temperature difference that the snowball sucked all the heat out of your hand to try and melt the snowball. And that's why your hand is cold. Not because cold came into your hand, but because heat left your hand. Now these reactions, all of them on table I, can be considered in the reverse direction. And this is important to note, because you will see this moving forward. So if we take 2 moles of NO2 gas and decompose them into 2 moles of oxygen and 1 mole of nitrogen, the reaction is going to be opposite, so it's going to be a minus 66.4 kilojoules when we go in the reverse direction. So the reverse reaction is going to release the 66.4 kilojoules of heat that were absorbed when the compound was originally formed. So this is an example of a reversible reaction, and most reactions given enough energy are reversible. Now the delta H, the heat value which was positive when the compound was formed, is now of negative delta H, indicated there. So the reverse reaction is considered exothermic. So that means we have a negative change in potential energy that results when potential energy stored in the substance undergoing whatever change we're talking about gets released into the surrounding environment as kinetic energy. So all the particles and matter that make up the surrounding environment start moving a little bit faster. Sometimes these are detectable, sometimes they're not. This is going to result in lower amounts of stored energy and a higher temperature in the surroundings due to that releasing of heat. And again, this is known as exothermic change. So on table I, we can figure out which one's exothermic by the negative heat value. And at the bottom of your table, there's a little blurb there that says, with a little star, that a negative value a minus sign indicates an exothermic reaction. So when we see that minus sign, it's going to tell us that that reaction is exothermic, which means the opposite's true. If it's a positive value, it would be endothermic. Now this is a physical change because what we're doing here is taking a solid compound and we're dissolving it into water. So when water is written above our yield arrow there, it means that we're going to dissolve this substance in water. And the AQ, we saw this from our first lesson in this unit. AQ means that we have an aqueous solution of Li plus and Br minus ions. And dissolving, since we can get the lithium bromide solid back by evaporating all the water, this is considered a physical change. But when this happens, it releases 48.83 kilojoules of heat, which gets released into the surrounding environment or into the water in our calorimeter, which causes the temperature of the water in the calorimeter to increase, or the temperature in the surrounding environment in general to increase. And we can reverse this reaction. We can evaporate the water, which is going to require an input of energy in order to get water to evaporate, turn from a liquid to a gas. It has to absorb energy, so this reverse is going to be a positive 48.83 kilojoules. And the water will get evaporated away and the ions will migrate back towards each other and they will become a crystal again. But in order to do that, we have to give 48.83 kilojoules back to the reaction in order to have it move in the reverse direction. Now the heat value, which was negative when the compound of lithium bromide dissolved, is now going to be a positive heat value, which would be endothermic. Now, the law of conservation of energy says that any potential energy that's lost by a change, whether physical or chemical, has to equal the kinetic energy gained by a measured mass of water in a calorimeter cup. Now, we looked at this briefly in our last lesson, and this is in a perfect environment. This is if we can insulate everything, and again, this is mostly in theory, because it is extremely difficult to insulate something and not lose any energy to the surrounding environment and have it all go from whatever the change is into the amount of water in the calorimeter. And if we have potential energy that's gained by change, that's going to equal the kinetic energy lost by the measured mass of water in the cup. So that would be a endothermic change, where the reaction or the change is taking in kinetic energy from the surrounding water or environment and storing it in the bonds of its molecules. This is going to cause the water, the temperature of the water or the surrounding environment to decrease. Now, specific heat capacity we discussed briefly in our last lesson, but specific heat capacity has to do with the rate at which a substance absorbs and releases heat. And I'll give you a good example of this. If you take a pot of water and you put it on the stove, you're going to boil some water for some pasta. We got a little burner here, and we got our little handles on the side of the pot. If you put this on here for, let's say, 5 minutes, okay, and you pull the pot off of the heat, and you touch the bottom of the pot, you think it's going to be hot or cold? If you thought hot, you're exactly right, because it was right in contact with the heat. Now, if we compare the pot to the water, and you stick your hand inside the water after 5 minutes of leaving the pot on the burner, do you think your hand could touch the water? You think it would be too hot, or you think you'd be okay? If you think you'd be fine, you're probably right. And that has to do with this property called specific heat. And in general, the specific heat of metals is very low, meaning it doesn't take a lot of energy to change the temperature of a metal. You could leave a spoon out in the sun for 5 minutes and it's going to get pretty hot. If you put a glass of water out in the sun for 5 minutes, it's probably not going to change its temperature much. And that's because of this relatively high specific heat capacity. And this is what's responsible for lake effect snow, among many other things. It's why we use water as a coolant, because it can absorb a lot of heat and it doesn't change its temperature very quickly when it does absorb a lot of heat. It also means the same for the opposite. Its temperature drops slowly as it slowly gives off heat. It doesn't happen quickly. If you were to fill up a warm bath, take a bath, come back in 6 hours, chances are the bathtub water is still going to be relatively warm. And that's because it's slowly dissipating all of its heat over time because of this high specific heat value, which again means that it takes 4.18 joules of heat to raise 1 gram of water by 1 degree Celsius. Now, the equation that we're going to use for this is found on table T, the back page of your reference table. And we have 4 different variables: Q, M, capital C, and a delta T. Now, one of these is given to you, the specific heat capacity. We generally are going to see these types of problems with water, some type of reaction occurring in a calorimeter. So we have a measured amount of water, and we're going to be monitoring the change in temperature of that water. So this value of our specific heat capacity is found on table B, on the front of your reference tables. The physical constants for water. and the specific heat capacity represented by C is listed there. The Q value is our heat value, or energy value, which is measured in the unit of joules, and it's how much heat is absorbed or released by whatever physical or chemical change we're looking at. M is the mass of water, and this we need to know specifically so we can figure out how much energy is being absorbed or released by using the specific heat capacity. So we need to know the exact mass of the water that surrounds our chemical or physical change. The change in temperature, which is the final temperature minus the initial temperature, is the temperature change of the water in the calorimeter cup that comes about as a result of the physical or chemical change. Now, we tend to see problems that deal with each of these four variables. Sometimes you do have to find what the specific heat of an unknown substance might be. Sometimes you have to find the final or initial temperature of the water before or after a reaction. Most often you're going to have to find how much energy was absorbed or lost. And we'll do a couple examples. So this is a reaction from Table I. We have a negative change in heat, which is going to indicate an exothermic reaction because it's negative. I want to make sure we understand that. Now, when you look at a reaction, you want to look at everything that we have here. We have solid carbon reacting with oxygen gas, and that's going to produce or yield, right? The arrow means yield, produce CO2 gas. And when there's no number in front of our species, we can assume that this is a 1 and a 1 and a 1. And we'll find that a lot of chemistry reactions are just like recipes. So this means that we need 1 mole of carbon to react with 1 mole of oxygen gas, which will yield us 1 mole of carbon dioxide gas. Now this reaction, if we carry it out in the calorimeter, is going to cause 50 grams of water to raise its temperature by 20 degrees Celsius. How much energy was released? Now we want to try and identify some key words that will kind of guide us to what we want to use, what equation or how we want to move forward in trying to figure out an answer here. So we have raising temperature, we have 50 grams of water, mass of water, we have calorimeter. This should direct you to the heat section on Table T on the back of your reference tables. And from there we can find that we can use our equation for calorimetry. Q equals mc delta T. Now I'd like you to define everything here. Once you decide what equation you're going to use. Now our heat value, that's what we're looking for. How much heat energy was released? So we don't know how much heat energy was released. We know that we have 50.0 grams of water. And since we're dealing with water, we know what the C, or the specific heat capacity, is. 4.18 joules per gram Kelvin. And this actually can be substituted for whatever temperature we have, but the temperatures have to be the same. In this case we have Celsius, so I'm going to call this joules per gram Celsius. We just want to make sure that whatever temperatures we have, that unit is the same, so our units will cancel. Now our change in temperature, well, we don't know the initial or the final, but we know that the temperature was raised by 20 degrees Celsius. And that's 20.0 degrees Celsius. Now we plug all these in right into our equation. So Q equals 50.0 grams times 4.18 joules per gram degrees Celsius times our delta T, which is going to be 20.0 degrees Celsius. When we punch all these in to our calculator, what we get is a value of 4,180 joules. Or we can call this, whoops, a daisy. We can call this okay, I'm not sure exactly what happened there. But we're going to want to round this to 3 sig figs. I'm going to call this 4.18 times 10 to the third joules. And that's a Q equals 4.18 times 10 to the third joules, or 4,180 joules. And there's our answer. Now for the next one, you guys want to pause the video and try this and check your work. I'd recommend that. We want to try and identify some key pieces of information here. We know that we're releasing. Okay. We're going to be releasing heat into the surroundings, 393.5 kilojoules into 25 grams of water in a calorimeter. So this should indicate calorimetry and our calorimetry equation, Q equals mc delta T. Now this reaction indicated by the negative sign means it's a negative delta H, negative change in heat, or an exothermic reaction. So this reaction is going to release heat and it's going to make the surrounding environment warmer. So since we're looking for the final temperature, and we know that the starting temperature, Ti, is 10 degrees Celsius and Tf is unknown, we know that since this reaction will release heat, that temperature of 10 degrees Celsius should increase. We know that the mass of water is 25.0 grams, and the specific heat capacity, since we're dealing with water, is 4.18 joules per gram. I'll do degrees Celsius because we're using degrees Celsius. Now the next thing we're missing is the Q value, which is given to us. We know that the reaction is releasing 393.5 kilojoules, but our specific heat capacity has energy in joules. So we have to convert this to joules. So a kilojoule to a joule is 3 spots. This becomes 393,500 joules. And once we have all those values, we can punch all this in. So the 393,500 equals mc delta T, or 25.0 grams, times the specific heat capacity, times the change in temperature. And what we get here is a delta T value of 3,766. And that'll be degrees Celsius. But we're not looking for the change in temperature, we're looking for what the final temperature is. Now that's the change. We know we started at 10 degrees, so we're going to add 10 degrees Celsius here, and we get as our final temperature. And that says TF there. So you've seen a couple examples of how we can use calorimetry to determine how much heat is being released, what the final or initial temperature is like of the water after a change. And we'll be using this specifically in lab. If you guys have any questions about what we did here today, make sure you come see me and ask them and get a little extra help. Have a great day.